Welcome everybody to the 16th event of the IAU Early Career Astronomer Online Discourse Series. My name is Maria Drazdowska and I serve as the co-chair of the IAU Working Group of Junior Members. I will be one of the moderators for today's event.
Hello, I'm Fatma Tatibi. I'm also the co-chair of the Junior Members Working Group, and I will be also the co-moderator of this talk. So today we have Dr. David Spergel with us. Thank you so much for taking up your time to share with us your knowledge and your experience. So I will start with your biography, which is long. So I had to pick a few things. And I encourage people to go on the Simons Foundation website to read more about you. So you spent 30 years at Princeton, and you are now the president of the Simons Foundation. But before that, you joined the Flatiron Institute, which is an internal research division of the Simons Foundation in 2016 as the founding director of the Center for Computational Astrophysics. Your research interests range from the search for planets around nearby stars to the shape of the universe. Dr. David Spergel is also the Charles Young Professor of Astronomy Emeritus on the class of 1897 Foundation at Princeton University. Oops. And, excuse me, and so I will start again. So he's the Charles Young Professor of Astronomy Emeritus on the class of 1897 Foundation at Princeton University, an associate faculty member in both the Department of Physics and the Department of Mechanical and Aerospace Engineering at Princeton, co-chair of the Global Coordination of Ground and Space Astrophysics Working Group of the International Astronomical Union, and co-chair of the Wide Field Infrared Survey Telescope Science Team. So this telescope will study the nature of dark energy, complete the demographic survey of extrasolar planets, characterize the atmospheres of nearby planets, and survey the universe with more than 100 times the field of view of the Hubble Space Telescope. Dr. David Spergel has played a significant role in designing the chronograph and in shaping the overall mission. He's one of the leaders of the Simons Observatory, which will include a planned millimeter wave telescope that will allow his team to take the next step in studying the microwave sky and probing the history of the universe. Recently, he has been active in the exploration of data from the Gaia satellite and observations made by Subaru's Hyper Supreme Cam. Using microwave background observation from the Wilkinson Microwave Anisotropy Probe and the Atacama Cosmology Telescope, Dr. Spergel has measured the age, shape, and composition of the universe. His observations have played a significant role in establishing the standard model of cosmology. And finally, Dr. David Spergel has received many prizes, a lot of prizes and awards for his work. He has more than 700 articles with over 100,000 citations, and he has won, for example, the Breakthrough Prize in 2018 and the NASA Exceptional Service Medal in 2017. Dr. David Spergel, the floor is yours.
Thank you. Everyone hear me clearly? Great. So I thought I'd start by giving you a little bit more about my career path. And it's interesting, when I sat down to write notes for myself on my career path, you realize that in some ways, the most interesting things I've done have built on things going wrong. They've built on failures. And I think that's an interesting sort of lesson in how we go along different paths. Like probably most of you, I had a long interest in astronomy. As a kid growing up, I read lots of popular astronomy books. I went to the local planetarium and then went on to study physics as an undergraduate, physics and astrophysics. I had the good fortune to work as an undergraduate with James Binney, who was then a young visiting faculty member at Princeton, and with Jill Knapp. And with Jill, I was able to go to the VLA back when it had only 7 antennas and do some observations of protoplanetary nebulae. I then went to Oxford for a year to work with James and to actually follow my then girlfriend. We broke up by the time we got to Oxford, but it ended up being an incredibly valuable year. I then went to Harvard, where I started working with Bill Press on thinking about dark matter. This was at a point at which we really started to understand that dark matter had to be something beyond atoms, and started thinking about what ways in which we can use astronomy as a laboratory for understanding the properties of dark matter. And it's, I think, often true when you come into an area with a new set of tools, you can do interesting things. So most people thinking about dark matter were coming at it with a physics background. I had a much more of an astronomy background. So realized that you could use things like the Earth's motion around the sun as the sun moved through the galaxy to produce an annual modulation effect, that the events, our velocity of the Earth relative to the dark matter is largest in June, is smallest in January, as the Earth moves around the sun and the sun moves through the galaxy. And that was, I think, the first really interesting thing I had done as a graduate student, was kind of taking my astronomy knowledge and bringing it into this area of physics. And it's one of these things that's obvious as a galactic astronomer, that you have to think about the Earth and sun moving through our galaxy. But if you come out of supersymmetry, that's not how you think about things. So I think for me, one of the lessons is if you come into an area with a new set of tools, that can be valuable. And I'll go back to that theme as I go through my trajectory. So I then went to the Institute for Advanced Study as a postdoc, and then moved on to Princeton as faculty. A lot of my early work as faculty at Princeton was thinking about ways in which we can form large-scale structure. And I thought about alternatives to the current popular inflationary models in which defects formed at phase transitions, ideas like cosmic strings or textures, would lead to the formation of large-scale structure, drive the fluctuations of the microwave background. And we spent about 5 years computing what these predictions would be. And then the COBE results came out. And I realized as soon as I saw the COBE data, that everything I worked on in the previous 5 years was ruled out. And while this could be viewed as an intellectual success, you want to be able to make predictions that are testable, the moment your model is ruled out, it's not a moment of happiness. And you then have to think what to do next. I then decided to organize a workshop on what the COBE results back then meant. And at the workshop, one of my colleagues got up and said that this means we must live in a flat universe. I didn't understand that, and it didn't make sense to me. So together, I felt part of that was driven by not knowing what the predictions were for an open universe and a closed universe. So with Mark Kamienkowski and Naoshi Nahara, we worked out the predictions of microwave background measurements for open and closed universes, and realized that by the position of the first peak in the microwave background spectrum would give us a determination of the geometry of the universe, and wrote a paper about this. And this excited the interest of Chuck Bennett and others who were putting together a proposal for a successor satellite to the COBE satellite. So perhaps for my most important turn was I was invited by this group to join the proposal, and we worked together and put together a proposal to NASA for a competition to select an Explorer mission that eventually became WMAP. And I then spent the next 5-6 years developing the theory and the analysis for the WMAP proposal. And the mission, like many, was delayed. I had arranged to take my sabbatical that year, so I would be ready to analyze the data. I found myself with a 1-year sabbatical and not quite nothing, but not the thing I planned to do, I couldn't do. So at that point, I decided to teach myself optics and start thinking about new problems. And I started thinking about how you could design a coronagraph to find extrasolar planets. And I gave that to myself as a kind of as a problem set problem. So I would understand optics. I was like teaching myself Born and Wolf over my sabbatical. And that actually led to a new chronograph design. And I think what I had brought to that problem was having been a cosmologist and used to thinking in Fourier space and used to thinking about Bessel functions and things like that. I had a set of tools that people who had thought about those problems before weren't as comfortable with. And that let me develop a new approach, these pupil coronagraphs, which have turned out to be useful in thinking about ways of doing coronography. After that, WMAP launched. I spent the next 9 years roughly working on CMB results. We got really terrific measurements. It was great working with an excellent team of people. A lot of the junior people who worked with me as graduate students and postdocs, we gave them the opportunity to lead on the project, and many of them are now senior leaders in the field, people like Ichiro Komatsu and Misha Verde and Haranya Pyrus, Olivier Doré, Rachel Bean, all kind of were young graduate students or postdocs working with us on that project. Having, at that point, done theoretical work, working with data, and actually designing an instrument, I was now a perfect candidate to be put on NASA committees. So I soon found myself on advisory committees and eventually became chair of the National Academy of Sciences Committee on Astronomy and Astrophysics. And in the US, we have this National Academy that was actually set up by Abe Lincoln to provide scientific advice for the government. And our job was to basically provide advice to NASA, advice to Congress, and so on. And this got me on a path where I found myself getting a call from John Grunsfeld soon after the decadal survey. Sorry, that's my mother beeping that she's in an Uber. It took a while to convince my 80-year-old mother that it's okay to go on an Uber. So I'm getting reports that it's okay. That's the occasional beeps you're hearing in the background. So I found myself in this role, and I got this call from John Grunsfeld saying NASA has just been offered a 2.4-meter telescope from the National Reconnaissance Organization, one they never launched. Could this be repurposed for an astronomy mission, and how could we use this? I think telescopes, we think of them as looking up. A lot of the technology has been developed by defense and spy agencies for looking down. That's true in many countries. That's certainly true of the US, Russia, China. So this telescope had been designed for looking down. The program was canceled and it was just sitting unused in a storage facility in upstate New York. So I then helped organize a series of workshops on how we might use this. It was a bit of an adventure doing that, and that NASA leadership did not want us to do this because they were afraid that this would lead to the astronomy community getting excited about building a new telescope, and they didn't want us to start anything before James Webb launched. And so we had a funny situation. It's a lesson in how bureaucracies work. where the very top of the organization didn't want us to do something, but people further down in the organization were quite supportive. So I made good use of the fact that I was a university professor and could do what I wanted at some level and didn't have to report to NASA hierarchy, and just organized meetings and generated some publicity and contacted people I got to know over time at the Washington Post and got good stories on this. And we were able to get the mission, which then was called WFIRST, is now called the Roman Space Telescope, started. And after we got that started, soon afterwards, it started to get canceled. And I found myself organizing groups of astronomers to go down to Washington to make the case in Congress to save the telescope. And I think every country's political system works differently with this. In the United States, while the president has a lot of power, the control of funding sits in Congress. And Congress is very protective of this. And just because the president cancels a project doesn't mean that Congress won't fund it. So we found ourselves going to Congress and making the case why it should be funded. And this is something where the younger members of the community were absolutely essential. Towards the end, during the Trump administration, when were canceled 4 times, we had about 100 people come to Washington, and a lot of them were graduate students and postdocs, people who I hope will be eventually the ones that will be using the data when the telescope is launched in 2026, and they've moved on along in their careers. And they came and met with individual members of Congress and their staff. And at least in our context here in the US, there's actually nothing more effective than an excited young astronomer who can go and say, I want this mission to happen, and this is why. And you tend, the way actually things work in many places, people represent a region. So if you have someone from University of Kansas who's going to talk to the staff from the senator from Kansas about why this national project is of interest to a graduate student in their state, or an undergraduate even in their state, that works really well. So I learned a lot of politics. This is definitely something I did not know about as an undergrad or graduate student, and found myself understanding a lot about how to get things done politically, and how to, by the time we got into our last year, I played a role in adding $500 million to the NASA budget so we could build the mission. And that's something that has, you don't think one can do, but over, enough cancellations, you learn how to do this. I'd say at this point in my career, I realized I had gotten interested in moving into what people sometimes call leadership positions. I'd done a lot as a researcher. I had a lot of students. I'd been department chair for a decade at Princeton and wanted to do the next thing. So I first found myself being considered first to become president of Princeton, and I was the runner-up. Then to become director of Space Telescope Science Institute, and I was the runner-up. And then felt, all right, I should try to look around for something new. At that point, I was approached by Jim Simons, so Jim's, who I now work for, is a very interesting guy. Jim's a mathematician by training. He's the Simons of Chern-Simons number. If you've ever learned anything about topology, it's a key concept. So he did some important work in math. He then inherited about $200,000, which is something, but not an incredible amount, and got interested in quantitative models of investing. He built the most successful investment firm and turned $200,000 into about 30 billion, of which he's taken half of and set aside to create a foundation to support basic research in math and science. And one of the things he wanted to do with that is build an institute. And he invited me to talk about what we might do in computational astrophysics. So I moved here to New York, and 5 years ago started a new institute, CCA. And that was a lot of fun to start from scratch and build a brand new institute. And we hired a bunch of people in joint positions and full-time and postdocs, and created visiting student programs, and just started all from scratch. And even through COVID, it was fun to be able to build and create something that I think has had an impact in computational astrophysics. And then about a year ago, Jim, who's 83, decided he wanted to retire from running the foundation. And he asked me to become president of the foundation. And that's been my new job. I've been in this office and doing this job now for about 7 weeks. This is my 7th week at the job. And I'm learning a tremendous amount. The foundation supports research in fields ranging from autism to oceanography, pure math, physics, of course, astronomy. We fund Quantum Magazine. We run a film studio supporting science films. We have an autism magazine. We support many different outreach programs. And I'm now supposed to figure out what to do next with this and direct this. And this is an exciting and interesting challenge. I feel a lot like I felt as a first-year graduate student, and I'd say also as a first-year assistant professor, where all of a sudden people start treating you like you know all these things that, and expect you to make decisions and choices, and it's all coming at you very quickly. And you're moving really quickly up the learning curve. And it's actually at times exhilarating and at times frightening experience. So that's basically been my career trajectory up to now. Been very fortunate in the opportunities. And one of the things this trajectory has brought me to is thinking about, and this will be now my transition to the rest of my comments, to thinking about open data and open codes. And I've thought about this in a couple hats on. One is I was the chair of the panel for the decadal survey this cycle on enabling foundations. What do we do to enable our research in astronomy? And it seemed to me that these were central things. And I've been co-chair of the IAU Commission on International Collaboration. And while we think of international collaboration sometimes in terms of the big telescopes we build together, like ALMA and SKA and James Webb, where many countries come together to contribute. I think in some ways, some of the most important things we do as a community is having open flow of data and the ability for people to work together and share and have access to it. An open flow of information. I would say actually in my Simons Foundation president hat, I think probably the most important thing we do for science in some ways is we fund the archive. So that's something that has this huge impact. Actually, it's huge impact at the grand scheme of things, relatively little money. It's about 2-3 million a year to support the archive. And well, that's not trivial. When you think about the billions we spend on science, the fact that the archive makes it accessible to everyone, I I think is a very valuable investment. And I think that's how I think about a lot of stuff with open data and codes is we have to make an investment to enable it, but its long-term impact is quite large. And, I think that this coming decade is going to be the decade of big data. We'll have surveys like the Vera Rubin Observatory, the Roman Telescope, Euclid, eROSITA, the Chinese Space Telescope, big radio surveys like Simon's Observatory that I'm involved in. These are going to produce these panoramic images of the sky. And I think if we adopt policies of open data and open codes with this, will enable the international community of astronomers to really produce transformative results that will not only impact astronomy, but serve as a model for the broader community on the advantages of the open flow of information. I think that's, we can affect the broader scientific and even world community by being a model of of openness. And I think that, if you look at the history of open data in astronomy, there's always been this tension between people who you build something, and I appreciate this having spent some of my career involved in building big missions. You invest a lot of time and energy into it, and you then say, well, then everyone's going to get the data. But I think the lesson has been the impact of the project is much greater if everyone gets the data. In some ways, some of the best example of this comes from the Japanese Xray program. The Japanese scientific community has had a program of launching major X-ray satellites around roughly every decade. They've launched now 6. And the first 2, the data was exclusive. The only people who got to see the data were those who built the instrument. With their 3rd and 4th and 5th telescopes, they then made the data publicly available. And the number of citations and the number of papers associated with the open data was 10 times the number associated with the closed data. And what that means for the people who build the telescope, right? And you invest all that time and they deserve lots of credit. They get credit for building something that has a big impact on the field. And since being at Princeton all those years, I was very much part of the Sloan process and see my colleagues and played some role in helping with that project. And the Sloan survey was much more impactful for providing open data for the world. And I think that lesson has not been lost. Gaia, the people who built Gaia got lots of credit for building it. They got some of the science out from the early design. But the fact that Gaia opened up its data to the world, I think has really changed the culture of astronomy. It enables people anywhere in the world to be on the cutting edge of astronomy. I think, to me, that's one of the great goals of the IAU, is to create an international community where wherever you are, you can make a contribution to advancing astronomy. And I think astronomy can be a model for other fields this way. I know here in the US, the astronomy open data policy from NASA for astronomy first spread to other areas of astronomy like earth science. And then in the Obama administration became a national policy for other fields to move to this idea that scientific data is meant to be open. And I think this should be an international model that if we produce scientific results, the data should be available so that we can verify it, right? I think if you make the data open, it enables people to work with it, and replicability and reproducibility are an essential part of the scientific method. And this open data, I think, in this era of modern data science is also a real opportunity and a real opportunity for the field, right? I think we could be providing to the data science community, the big data community, a valuable data set more broadly. astronomical data for data science has a number of advantages. The data is open access. It has no commercial value. It's actually free of a lot of the ethical issues associated with a lot of the data like images of faces that often get used for surveillance and things like that. So when people develop these technologies, they have dual use, and some usages are not things that we want to have happen. Astronomical data is rich. It's images, tables, graphs, uneven time series, multidimensional grids. And it's data, and broadly data in the physical sciences, and something I've been working on a lot last couple of years is highly structured. We have individual particles or planets or stars interacting in particular ways with well understood symmetries. Data structures that differently from the kind of widely studied images and sequences in big data. And this rich data structure has really inspired a lot of the work in graphical neural nets and geometric deep learning. And something I've been sort of the focus of my own work over the last few years has been the fact that we can produce these high fidelity simulations that capture causal models of astronomical phenomena, like the evolution of large scale structure, planetary orbits. We can model the astronomical processes like gravitational lensing. And then we can develop techniques like likelihood-free inference, density estimation, implicit general models to model this. And the techniques that are being developed in astronomy have actually now spread into other areas like particle physics and chemistry and neuroscience. And because we have models where we can simulate data, we can look at things like overfitting, we can make contributions to understanding interpretability. It can have significant impact. And I think it's really a two-way street. Of course, we bring these things to data science. Data science is giving us new tools. I think machine learning is going to play a significant role in analyzing these data that we're talking about, potentially producing transformative discoveries, seeing things like AlphaFolds results from DeepMind shows some of the potential power of machine learning to do transformative science. And I think also the fact that we can do interesting machine learning, it matters for all of us, but I think particularly for the junior members, provides a richer set of career paths, right? So that I know many of my, a whole bunch of my former students are researchers in astronomy and have pursued careers in that direction, but a lot of people are now pursuing careers in data science and having, one of my students, Sudeep Das, who worked on analyzing microwave background data, realized when he left academia that the techniques he was using for working with finding eigenvalues and eigenvectors in very big sparse data sets could be used at his new job, working at Netflix, making predictions on what, if you like X, you will like Y. So those of you who use Netflix and get those predictions, he's the head of the data science group that does that. And you can think about all of your movie preferences of millions and millions of people and 10,000s or hundreds of movies as a very large, sparse, non-square matrix. And the stuff he did in his thesis is immediately applied in telling you which movies you like. So that's an application of astronomical research that you probably don't realize is out there, but your Netflix movie predictions my former student Sudeep contributes to that. So in addition to open data, I think another important frontier is really open codes. I think it's important for reproducibility of simulations and verification that codes can be tested. I think it's also important for their extension. Codes that are open get built on and extended by others. And I think whether you're looking like analysis codes like AstroPy, a code like MESA, which I think has had an enormous impact in opening up stellar evolution as a field. It's made it a much, when I was a graduate student, I really thought of stellar evolution as a backwater. People wrote those codes in the 50s and 60s, and there were these ancient Fortran codes that no one knew how to use except for the authors. And now there's just really great work being done and lots of people contributing ideas and building on it. And I think the fact that Mesa was built as an open structure has had a really important intellectual impact on the field of stellar evolution. I think the fact that going actually back to work by Sverre Arseth, who wrote these early n-body codes and made them public, I think that really helped shape the development of the fields. So I see a complement to open data as open codes. And, I think we want to figure out ways to foster this culture of openness, encouraging a social norm of sharing and collaboration with codes. I think to do that, we're going to have to provide the right incentives for open source software, whether that's targeted grants that fund people and recognize the importance of supporting codes, right? Supporting things like developing codes like AstroPi. Kind of honoring people who do the work that make the open code. So whether that means funding, jobs, prizes, citations. I think it's really important that we cite and reference people whose codes we use as we build the pieces of the work we do, because in our worlds, citations and references of various kinds are one of the ways in which we get credit. I think we need to view software development and code maintenance as a cost, and recognize that software engineering is going to be a piece of our education. And that's something that, I think we need to evolve our undergrad and graduate education. That I think for many people, having some software engineering skills is as important as a strong grounding in physics and mathematics. And not all, graduate programs are often slow in catching up on this. And one of the things that I'm hoping we're going to do more of at Flatiron, or to make things available. I hope it's something that I've talked with Evine about this at the IAU, that the IAU can do more, and it'd be great for the junior members to be thinking about what will be most useful for them. Is, what are the software tools and training we need? Because it's something that often isn't part of graduate training programs, and is something that's evolving with time. This is an area where I think the IAU can potentially play a role, really at least as a central place to learn. Like, where do I learn the codes I need to work with data from ALMA or upcoming data from JWST? And I think that's an important role for us to play. One of my own priorities for the coming years, and something I've been working towards, is trying to get, this goes back to something I talked about earlier, the big data sets that will be coming from Vera Rubin and Roman and Euclid, and also from China, the Chinese astronomers are going to be playing an increasingly important role in helping to drive the field in the coming decades, and that they become part of this world of open data. And India's joining. There's more and more places producing valuable large data sets, and I think we all benefit when we become part of this culture of open data and open codes. And I think the IAU can play a significant role in being the place where we come together and propagate and build this value of openness. So let me stop there and thank you for listening, and to open it up for comments and questions and thoughts. Thanks.
Thank you so much for this talk. So we received some questions from the audience. And the first one is about data access and code sharing. Do you know how it varies from across astronomy fields?
I think there's real variation across fields. So let's take code sharing. You can take an area like stellar evolution, where the MESA code is widely used and is all open and people share codes. The supernova community is generally private codes. So if you want to do simulations of a supernova explosion, that requires working with individual people who develop those codes, and they're proprietary. And while I appreciate it takes lots of time to develop those codes, I think the lessons have been that subfields in which codes are shared move more quickly. In cosmology, well, one of the things we've been trying to do here is make open big simulations. So, you know, we've done these big suite of simulations, these Quixote simulations that are all of it, you know, it's a petabyte of data that we've made available and accessible. And its impact is much larger because we've made those open, right? We've done that in the last couple of years. It really varies if you look at this from subfield to subfield. In the theory side, fluid dynamics codes like Daedalus are public. Plasma physics codes coming out of heliophysics tend to be proprietary. People tend to own them. So some of this is generational. I think on average, younger people are more supportive of open codes. So with time, as the code developers get younger, I think people have seen the impact of open codes and are shifting that way. And then on the analysis side, things like AstroPy have been very helpful in providing open codes. And something I'm most familiar with both NASA and ESA policy, where they require, if you're developing codes to support a mission, often a lot of that code in databases are available. So on the ESA side, the two I know best are Planck and Gaia. The Planck team made all of their codes available. As someone who was not part of the Planck team, I was able to go in, read the codes, extend them, able to actually find some improvements on how things could be done that they took advantage of. We did the same with WMAP. We made all of our codes available, and others went and looked at what we did and found ways to do it better, and we all benefited. We then did our next analyses building on their algorithms. So I think when codes have gone open, the people who've developed them benefit.
If I may follow up on this. So my field of research is astrochemistry, and I think it's clear. I think there's no need to debate the point that if your code's public, you will have more people using, you will have more citations. And naively, everybody wants other people to use their code because their code is the best. But then on the other hand, there's also this fear that I've gathered in my field that if you make your code public, then people will misuse it, produce crazy results, publish that, and then it essentially kind of goes under the name of your code. Do you have anything to kind of comment this and how to mend these concerns, that people won't go abuse what you make public?
When people publish wrong results with codes they don't understand, it's the blame is not on the code developer. It's their responsibility. Now, it is good to write guides. It is good to let people know, and I think in astrochemistry code, you can really imagine warning labels that come up and say, this code does not work in this regime of temperature and density, right? There's some flags you put in, right, where you can warn people. Another piece of my experience with the WMAP data was we put everything out there, and analyses that people did of our data, right? We had like 100,000 some huge number of citations to WMAP papers, right? So people did lots with it. Some people did analyses that were like fine and kind of found the same things we did. Some people did analyses that extended what we did. And some people did analyses that were wrong. And the analyses that were wrong, if they were wrong in interesting ways, often the people on the team and the code developers get to be the ones who are the referees. So you often are actually in the position to be the one that looks at and says, and then this becomes, I think, both in your interest and an obligation, right? Why don't you get the paper to referee and say, why don't you do these tests? And I think there's also a chance if you make your codes public, and I think the people who do this benefit from this a lot, is to run workshops and summer schools and, go on the codes. The Mesa folks have done a great job running summer schools like that. We just ran a summer school here this past, that just ended on using some galactic dynamics codes. And I think the way I would go forward in astrochemistry if I was developing a code there is run some workshops, build a Python notebook to train people, to get them started. That will get, you'll develop, having a sophisticated user community will mean people will take the work and extend it and add their codes, and both the developers and the field as a whole benefit. So I think investments in doing that are beneficial. And I think they're, in terms of some, career advice for junior people who've developed those codes and run those schools and get associated with that, people using their codes and algorithms do this, become viewed as and do become the leaders of the field, right? And then get good offers and opportunities usually to build on the work they're doing and recognize an opportunity. So I think that's kind of the way forward to go with open codes.
Thank you. We have a question from John F. Wu. Do you see private foundations as a complement to government public entities for funding basic science research? Is there any danger?
Sorry.
No.
Go on.
Is there any danger with large donors dominating the direction of science research, possibly towards their own interests?
Yeah, I think the thing to keep in mind is for science funding as a whole in the US, where I know the numbers, foundations are about 4% of science funding. So it's significant, but the overall directions are set by the national agencies. And I think the roles of science foundations are to be complementary and to do things that are harder for national agencies to do. And, let me give 4 examples of things that I think have been kind of successes by foundations. Government agencies tend to fund big things that the whole community has bought into. And review processes tend to reward things that are, you've done X and we take the next step. So foundations can support riskier things. So the Sloan survey was supported by the Sloan Foundation at a time at which people weren't doing big surveys, and building a dedicated telescope rather than a multi-purpose telescope was not a usual way to go. And it was, I think, the vision of the people who proposed it and the vision of the people at the Sloan Foundation, the fact that there was a way of funding that was different from the standard National Science Foundation route here, enabled that to happen. Another is foundations can make commitments, which governments often won't, agencies won't do, to long-term funding. So we've made this long-term commitment to support the archive at the Simons Foundation. And I think that long-term stability can be quite important. One of the things I'm setting up now that I think would be very hard for a government agency to fund is a set of fellowships that are aimed at mid-career people that we're calling pivot fellowships, that fund people to make really radical changes in their career direction. So to fund someone who's been a physicist their whole career to move into epidemiology or neuroscience, to fund a chemist to move into cancer research, to really allow these large changes, which are basically impossible to get funded through a federal agency that tends to be very mission and goal driven. And so I think we can do well there. And often one can do riskier things. I think the Rubin telescope is a good example where before the decadal survey in the US recommended it, no federal agency would give them money. But it was hard to get recommended until you can show that the technology worked. And $50 million in foundation funding enabled them to develop the technology to the level at which they could then get nearly $1 billion in federal funding. So it could often be this kind of early money that absorbs risk. And we're looking, I mean, I know some of the things we're looking at doing in the next few years, and they're much riskier. I think one advantage we have is we can stop doing things more easily. So we can take risks, try something, and then if we build a new set of instruments that don't work, we're not committed to their long-term support. And generally speaking, our trustees who we report to understand our role is to do riskier things. A message I've been telling people as foundation president is if some of our projects aren't failing, we're not taking enough risks.
Hi, Professor David. I follow your work. I have a question related with the H0 value that has this controversial thing. I know that you are involved in both sides. So I would like to know your opinion about this controversy, this difference in the H0 value. It's a cosmological problem of the model or more in the data analysis in one of the measurements, no? What do you think?
I'm open to both possibilities, right? So, I mean, if you had asked me 6 years ago, I'd say it was one of three possibilities. It was either a problem in the microwave background and large-scale structure measurements. It was a problem in the local distance measurements, the Cepheids, or something missing in our model. At this point, I think it's the latter two, one of the latter two. I think between having measurements now from Planck and ground-based measurements like ACT and SPT, large-scale structure measurements, they're all giving values of H0 of like 68 to 69 kilometers per second per megaparsec. I actually think it's a little bit on the higher side, more likely 69 than 68, but that's the Cepheids, that group continues to get a high value. Cepheids are hard. The fields are very crowded. They do I do worry that there could be some systematic issues there. It is intriguing that gravitational lensing and tip of the red giant branch, find values more consistent with the cosmological ones, and that may be the resolution. This is a field where the best solution is to get better data. So I think we can look forward to more LIGO events and having a completely alternative route there. And I'm also very excited about JWST because it's going to be able to do tip of the red giant branch to much larger distances with a much bigger sample. And I think once we've got, it's 4 or 5 years from now, we've got a bunch of tip of the red giant branch observations from JWST. Either the problem goes away or it gets even more intense, and that would be the most exciting. In my theorist hat, I've dabbled with a bunch of ideas on what it could be. I think the thing that would be most consistent with the data is to add some new physics that changes the expansion rate or the way that sound waves move in the early universe. The way I think about the way we measure H0 cosmologically. Here we go. I look at my microwave background map and I get a characteristic size for hot and cold spots. That characteristic size is set by the distance a sound wave moves in the between the beginning of the universe and recombination, and that gives me a ruler. So I have to change that ruler to change the value of H0. And the way to change that is either change the way sound waves move or change the expansion history. So that requires either something like early dark energy or change the way some component behaves. Neutrinos are the sector we know least about, so you can add neutrino-neutrino interactions, do something there. The exciting thing to me about that early dark energy and neutrino-neutrino interactions is that they change the predictions for the microwave background at high multiples, which is exactly where our data is getting better. And now I have to put my hat on of, I'm involved in collaborations that are looking at this, and we have not yet published our results, but we are actually looking at some of these models and testing them with data that's coming in. And, I think these, it's an exciting problem to think about because it's something where I think we can point to and say, 5 years from now, our understanding will be better. The large scale structure data is getting better. Microwave background data is getting better. Our local distance indicators are getting better. And people have, over the past decade, as this problem's gotten more interesting, developed novel ideas that would point to new physics, like early dark energy, neutrino-neutrino scattering, that could be what's going on here. And, most of the time when there's an anomaly, data improves and goes away. But sometimes, I remember this anomaly when I first started out as a graduate student, that the large scale structure data didn't fit the then popular model. And the only way to make it fit was to add dark energy. And our particle physics colleagues said dark energy was crazy. But it seems to be there. So, sometimes we find new things.
Hi, I have a question more on the societal impact side of things. So I study supernovae. My colleagues and I seem very supportive of open codes. However, there's always kind of the unsettling thought that explosion modeling can be used for other purposes, that public codes can be repurposed for Department of Defense, organizations like this studying explosions here on Earth. So I'm wondering just what your thoughts on that are.
They already have the codes. Right, they have the codes. The algorithms are public. They're not limited by their ability for code development. I mean, the issue for nuclear proliferation is uranium separation. Right. That's most, well, if the two issues for proliferation are code separation and manufacturability of appropriate explosives. And those are not really near the code development. It doesn't touch those problems. You know, you can, it's 11 o'clock. I can talk about nuclear proliferation issues, but it's a whole other direction.
Sure, thank you.
David, thank you so much. We have indeed run out of time for further questions. Thank you for your time. Thank you for sharing your opinion with us. And thank you for promoting this openness in astronomy. Personally, I also agree with this direction. I think it's the right way forward. So a round of applause. Thank you.
Thank you so much.
Great, thanks for listening and enjoy the rest of the meeting. Hope the next big IAU meeting will be in person, and we'll see many of you there.
Thank you again.
Thank you.
Thank you.
Bye-bye.
Bye-bye.